Hi everyone. Today we will discuss Kirchhoff's rule or Kirchhoff's laws. There are two laws, the first law and the second law. The first law is termed as the point rule. Now this point rule states that in any circuit, whether it is a closed circuit or an open circuit, the sum of current at any point, and that point can be considered as a junction. The sum of current at any point, it is zero. This means, suppose if you take any point, now let us take this example. This is part of any circuit. Okay, some currents are coming from this side, some current is going from this side, again current is coming from this side, similarly it is coming from this side going out of this with respect to this point, similarly current is coming here and current is coming here. Okay, coming from this side. So some of the currents is moving toward this point and some of the currents it is moving away from the point. So this is just part of any circuit. Now this rule is applicable for a closed circuit as well as it is applicable for any open circuit. So here when we consider the summation of current at a point is zero, and we can observe that some current are incoming current and some currents are outgoing current. This will be possible only when we consider a sign convention. So incoming current it is taken with the positive sign, outgoing current it is taken with the negative sign. So if we use this concept, so here we can just see that this I1 it is incoming, so it will be taken with the positive sign. I2 it is incoming, positive sign. I3 it is outgoing, so it is negative sign. I4 again it is incoming, so again it will be positive. I5 again it is incoming, so positive, and I6 is again incoming, so it is positive, and I7 it is outgoing, so it will be taken with the negative sign. So we can consider that I1 plus I2, because I1 and I2 both are incoming with respect to this point. I3 is outgoing, so minus of I3. I4 is again incoming, so plus I4. I5 is again incoming, so plus 5. I6 is incoming with plus 6. And I7 is outgoing, so minus of I7. So sum of all these currents, it should be equal to how much? 0. So summation of this, it is 0. So again, if you simplify, so I1 plus I2 minus I3 plus I4 plus I5 plus I6 minus I7, it is equal to 0. So this gives you that I1 plus I2 plus I4 plus I5 plus I6, that is equal to I3 is here with the minus sign, I7, so this will come this side, so it is I3 plus I7. So these are all incoming current, this is outgoing, so either we can say summation of current at a point is 0, or sum of incoming current it is equal to sum of outgoing current. So this way we can develop these equations. Now this concept, it is nothing but it simply justifies the conservation of charge. We know that charge is quantized and charge is always conserved. So total charge is always conserved. So if we use this relation that the total charge is conserved, that is Q is constant, or summation of Q is constant or it is conserved. Differentiate both the sides with respect to time t. So d sum of this Q divided with respect to dt is equal to dc with respect to time t, dc upon dt. First order differentiation of a constant, it is always 0, so this is equated to 0. dq upon dt, we know it is current. Rate of change of charge, it is current. So it is sum of I is 0. So from here we get this relation, and this was observed by Kirchhoff, so it is termed as Kirchhoff's rule or Kirchhoff's law. So summation of current at any point, whether it is part of the circuit or it is a closed circuit, that is always 0. So if we consider a circuit, let us consider a circuit. suppose you consider this circuit, let us say resistance R1, this is EMF E1, this is R2, this is E2, this is R3, and this is suppose E3. Now, consider this I1 from here, I2 from here, and I3 from here. This is just my assumption. The direction of current, it can be in any direction. Exactly that we will be able to understand when we simplify the circuit. But it is just for our purpose. I have assumed that I1 is flowing in this branch, I2 is flowing in this branch, and I3 is flowing in this branch. So if you consider, suppose this point, just for our understanding. So this I1 is coming here. This I2 is coming here, and this I3 is coming here. Okay, now this gives you that I1 incoming, I2 incoming, and I3 incoming. All three are positive. I1 plus I2 plus I3. That simply means what? Sum of this incoming current. Is it possible that sum of three positive quantity is zero? Sum of three positive quantity can never be zero. So it means my observation here or my assumption here, it is wrong. So this rule gives you how to distribute the current in a circuit. That is the main part as far as the application of this law is concerned. How to distribute the current in a circuit, because summation of current is zero. So when sum of current or summation of current at a point it is zero, it means sum of the current has to be inward and sum of the currents has to be in the outward direction. So if some of the currents are in the inward direction, so some of the current, because here I have assumed all incoming current with respect to this point, that does not justify this, because sum of three positive quantities or sum of any number of positive quantity, it can't be zero. It means out of this I1, I2, I3, at least one of this will have in the opposite direction. So if I consider suppose I1 this side, I2 this side, then I have to consider I3 this side. Then sum of these two incoming minus this outgoing, then only sum of those three quantities it can be zero. So now I can write I1 plus I2 minus I3 is equal to 0. So because here I1 it becomes incoming, I2 incoming, but I3 is outgoing. So I can say I1 plus I2 plus minus of I3, that is 0. So from the first rule, we conclude as far as the distribution of the current in any circuit, whether it is a simple circuit or it is very complicated circuit, that is justified as far as the first rule is concerned. So if you can't distribute the current properly, or if you don't distribute the currents properly, you will not be able to simplify the circuit and you will get the wrong result. So from here we can conclude how to distribute the current. So whatever be the point chosen as far as the distribution of a current in a circuit is concerned, whatever is your circuit, whatever is the point chosen, you distribute the current in such a manner that some of the currents are in the inward direction and some of the currents are in the outward direction. Then only this rule, or you can say this rule, it will be satisfied or justified. So whenever distribution of current takes place, we always keep in mind that the first rule, as far as the Kirchhoff's first rule is concerned, it is justified. And once it is justified, it means your distribution is correct. Then only you can proceed further to simplify the circuit. Now let us see the second rule. Now the second law says the algebraic sum of all the voltage drop around any loop in a circuit must be 0, or the sum of all potential differences across all resistances should be equal to the sum of all EMFs. Means if you consider suppose any circuit, so here if you consider suppose R1, R2, E1 and E2. E1 and E2, they are the EMFs of these cells. Okay, and R1, R2, they are external resistances. There may be some internal resistance of this cell as well as this cell. Let us assume R1 as well as R2. Now if you consider the distribution of the current, suppose the current is flowing in this circuit in this direction. So once the current flows in the circuit, so there will be potential drop across this resistance, potential drop across the internal resistance of the cell, similarly this resistance as well as this resistance. So this law says sum of all potential difference. So when we say sum of all the potential difference, that means the potential drop across the resistances as well as potential drop across the terminals of the cell, that should be equal to 0. So either we consider this statement of this law, or we say sum of potential difference across all these resistances, that should be equal to sum of all EMFs. It should be equal to sum of all the EMFs. So statement is same, only thing is the sign convention, it will be different. So here we will consider the sum of potential difference across all resistances, it should be equal to sum of all EMFs. So we will try to solve all problems based on this statement. Either you can consider sum of all potential difference, it should be equal to 0. When we say sum of all potential difference equal to 0, that means potential difference across all the resistances plus potential difference across the terminals of the cell. Because E1 and E2, they are the EMFs. EMF means the maximum energy that it can generate. But once there are internal resistances of the cell, suppose R1 and R2, depending on the direction of the flow of current or from the cells E1 and E2, either the potential drop, either the EMF of the cells, it will increase or it will decrease. If it is suppose charging of the cell, the potential difference will increase. If it is discharging of the cell, it means the potential drop will decrease. Now when we say charging or discharging, it means this is suppose the lower potential side and this is the higher potential side. If the current is going towards the higher potential side, let us say in this direction, it means this cell is being charged. If the current is coming out, like here I have assumed current this side, it means the current is coming out of the cell, it means this cell EMF or the potential, it will decrease. This current is going towards this, so it is being charged. So E2 here it is being charged, E1 is getting discharged. From the conservation of energy, the total energy that will remain constant, okay, or it is always conserved. So using all these concepts behind this law, we will say that the sum of potential difference across all the resistances, when we say across all the resistances it is 0, that means R1 and R2 are the internal resistances of the cell. Because of that, this E1 and E2, either it will increase or it will decrease, so that it will generate a potential difference across the terminals of the cell. So taking consideration of all the potential in this circuit, whether it is the cell or whether it is the resistances, sum of that is 0. So that is the first part of this statement. Second part says sum of potential difference, it is equal to sum of all EMFs. Yani potential difference across the resistances, whether it is your external resistance or whether it is the internal resistance R1 and R2, sum of that it is equal to sum of all EMFs E1 and E2. So you can follow any of the statement. Only thing is you need to have different sign convention. So we will follow the second part of this, the sum of potential difference it is equal to sum of all the EMFs, and we will try to simplify, because this statement as far as the sign convention is concerned, it is less confusing, and that's why we will follow this statement. Now here, if you consider suppose this circuit, let us say again this is part of any circuit. You have a current is coming from this side. So current here is on that coming from this side, it means this side also there is some circuit. This side also there is some circuit, this side also there is some circuit, again some circuit and some circuit, such that some current is coming from this side also, some current coming from this side, and so on. Okay. So either it can be part of any closed circuit or a bigger circuit, or it can be simple this circuit. Okay. Now let us analyze and develop the circuit equation. When we say summation of IR is equal to sum of all EMF, so that will be termed as a circuit equation. So using the first law, that is summation of current at a point equal to 0, and sum of potential difference, that means I into R is equal to sum of all EMFs, means summation of all E's. Okay, so just simplifying these two equations, based on the circuit, we will be able to calculate whatever the unknown quantities, and the unknown quantities will be what? The flow of current in different branches of the circuit, the potential drop across the resistances, potential difference across the terminals of the cells. So these are the generally unknown quantities, and just simplifying this we can calculate on that. So once the distribution of the current is concerned, so we will consider the first law, circuit equation that will be generated based on the concept of second law. So here if we consider this, so some current is coming from this side, so that current I1 is flowing. Here you can see current I1 is flowing in this direction, in this branch. Similarly, some current has again come from this side, so that the current value in this it has become I2, but it is coming in this direction because some current is coming from this side, some current coming from this side. So in a branch, there will be only one direction of motion as far as the current is concerned, either from left to right or from right to left, or in the clockwise direction or in the anti-clockwise direction. It cannot be in the two different directions. Okay, so I2 has been taken in this direction. Similarly, this is your I3 again. This side it is I3 in this direction, this side it is I4 in this direction, and so on. So whether your distribution of the current, that is the direction of distribution of the current, whether it is correct or not, that is based on Kirchhoff's first rule, because those directions should be taken in such a manner that sum of current it should be zero. It means some of the current has to be taken in the inward direction, some of the currents in the outward direction, then only the sum it can be zero. Otherwise, if you take only in one direction, then it becomes sum of all positive quantities, and sum of all positive quantities can never be zero. So let us analyze this. So here, this is your I1, this is I2, this is I3, and this is I4. Now consider this circuit. So if you consider this circuit, and we are taking clockwise direction as positive, we are moving such a way that the clockwise we are taking positive, anti-clockwise it will be taken with the negative sign. Now before I discuss this equation, just see the sign convention. The sign convention we take on the basis of tendency of the cell to release the current. First, we choose a path. As far as when you generate the circuit equation, we move in the circuit. Let us say this is your circuit, okay, containing resistance, EMF, and so on. This is your point A, B, C, D, E. So if you take the circuit, so we will consider the circuit as A, B, C, D, E. So this becomes your closed circuit, starting from the point A, finishing at the point A. So this gives you the closed circuit. So that becomes A, B, C, D, A. If you consider only A, B, C, D, that means it remains open circuit. And we can consider the flow of current in an open circuit. Current will always flow in the closed circuit. Or if you see some current coming from this side, so don't get confused that it is open, so how the current is just shown here, and it is part of some other circuit. That's why some current is coming from this side. So always it will flow in the closed circuit. Closed circuit means starting from this point, we have to come back to the same point. So circuit name is A, B, C, D, A. Now when we consider A, B, C, D, A, the path chosen is from A to B, from B to C, C to D, and D to A. Now if you are moving strictly according to your path chosen in the circuit, take the current, whatever current is flowing in this direction, this path chosen, just to avoid any confusion as far as the sign is concerned, whether it is your plus IR, sign of the IR, or whether it is sign of EMFs. Strictly choose a path and strictly move according to the path. So A to, if your current, distributed current flows from A to B, and the path chosen is also from A to B, it means take that current with the positive sign. Now, tendency of the cell to release the current, because we exactly don't know which cell will release current in which direction. Till we completely simplify the circuit, we will not be able to say in which part of the circuit current is flowing in which direction. So these are just our assumption. I1 in this side, I2 this side, I3 this side, I4 this side. These are just assumption. Exactly we don't know whether I1 will be flowing in this direction, I2 will be flowing in this direction, or so on. So based on our assumption, if your assumed current is moving along the path chosen, take that current with the positive sign. If the tendency of the cell to release the current, again, which cell will actually release the current in which direction, again, that we don't know. Right at this stage without simplifying the problem. But tendency to release the current, that is known to us, because every cell has the tendency to release current from the higher potential towards the lower potential, from higher potential to the lower potential. That is the tendency. Actually, what will happen, that we can understand only after simplifying the entire problem. So if tendency of the cell to release current is also strictly according to the path, take that EMF also with the positive sign. If it is in the opposite direction, take it with the minus sign. So again, just to summarize this, first we have to take a path, choose a path, current, then distribute. First step is distribute the current. Second step, consider a path. If distributed current is moving along the path chosen, take it with the positive sign. The tendency to release the current from the cell is also in the same direction of the chosen path. Take that also with the positive sign. If they are in the opposite direction of the chosen path, take them with the negative sign. So we will follow this sign convention and we will develop the circuit equations. So here, let us say I am moving with the path A, B, C, D, E, and E. It means your path is A, B, C, D, E, E. So starting from this point A and finally coming back to the point A. So here if you consider, so here this is I1. So I1, R1. So you can see this I1, R1 is in the same direction of this path A to B. So A to B. So I1, R1, it is taken with the positive sign. Next is B to C. From the path B to C, the current is moving from C to B. This is the direction of your I2, C to B. So current is flowing from C to B, but path chosen is from B to C. So it means it should be taken with what? Minus sign. So minus of I2, R2. Plus I3, R3. Here you have this I3. Okay, and this is R3. So I3 is also in this direction, and path is from what? D to E. You can see this D to E. Now in this part we are not considering C to D because there are no resistances. So when there is no resistance, it means we don't have to bother about I into that R. So from this D to E, so D to E. So current path is from D to E and the current is also from D to E. So it means it will be taken with the positive sign. So plus I3, R3. Next is this I4. Again, path chosen is from E to A. So E to A. I4 is also in the same direction, that is from E to A. So again, that is taken with the positive sign. I4 and R4 is equal to. Now see this. Here it is E1. This is your E1. This side is the higher potential of this E1 and this side is the lower. So it has the tendency, not the actual direction. It has the tendency to release current in this direction from the higher potential to the lower potential inside the circuit, not the outside circuit. We have nothing to do with the outside circuit. Inside the circuit from higher to lower this. This is also from higher to lower, but this is outside the circuit and we have nothing to do as far as the outside part is concerned. So inside the circuit, it is from the higher potential toward the lower potential. So it has the tendency to release current in this direction. But we are moving from what? C to D. You can see C to D. This is the path chosen. A, B, C, D, E, A. So it means it is in the tendency to release current by this cell is in the opposite direction of our assumption. So it is taken with the minus E1. Next is E2. So E2, again this side is higher and this side is lower. So higher to lower means again this direction. This direction, higher to lower, it means in this direction. And current, the path is also from D to E, that you can see. So it is in the same direction of the path chosen. So it will be taken with the positive sign, so plus E2. Next is your E3. So again, if you take this E3, so see here, E3, this side is higher and this side is lower. So this side, so again, it has tendency to release current in this side, in this direction. But we will be moving from E to A, and it has tendency to release current from A to E. So again, in the opposite direction, so minus of this E3. So this justifies, and this gives you this circuit equation. So I1 R1 minus I2 R2 plus I3 R3 plus I4 R4, that is minus E1 plus E2 minus E3. So this way we can develop the circuit equation. Sum of all currents at a point is 0. So using that, so I should remove this. So sum of current, the second equation that you can generate is sum of current at a point, it is 0. So you can consider suppose this point. With respect to this point, I1 is moving away from this, I4 is going towards this. So we can consider minus I1 and plus I4. Again, with plus this current. This current is suppose I, let us say I. So here, this is equal to out. With respect to this point, this is incoming, this is outgoing, and this is again incoming. So some current I, if it is coming from this side, then that I is equal to minus I1 plus this I4. So this gives you the distribution of the current as far as this point is concerned. Similarly, you can consider this point, this point, this point, and you can develop the equations, whatever is required to simplify the question. So this is your circuit equation. Simplifying this, we can calculate or we can proceed further. Here you can see this A, B, C, D, E. This is your path chosen, and based on this, we have considered if the current is moving strictly according to the path chosen, it means that will be taken with the positive sign. Cell is having the tendency to release current in the direction of the path chosen, that EMF will be taken with the positive sign, otherwise in the opposite directions or with the negative sign. So let us take some more example. So here if I take this circuit, so suppose this is the circuit. Here we have this external resistance R1, EMF of the cell is E1, and internal resistance of the cell is suppose R1, small R1. This is suppose R2, this is E2, and this is R2. Again, this is R3, E3, and R3. So first we need to distribute the current. Now as far as the distribution of the current is concerned, don't get confused from where should you start distribution of the current. It is up to you to start from any point. Don't consider the value of the EMFs E1, E2 or E3, whether E1 is greater than E2, E2 greater than E3 or so on. Similarly, there is no need to consider if the magnitudes of the R1, R2, R3, E1, E2, E3 or small R1, R2 and R3, even if it is given, there is no need to check which one is greater or which one is smaller. So simply we have to consider as far as the direction or distribution of the flow of current is concerned, it is up to you to assume. From any point, you can assume. Generally, we know that the tendency of the cell to release current, it is from the higher potential towards the lower potential. Ignoring this, you can also consider or you can also assume the current flowing from the lower potential to the higher potential. All these are just assumption, and we are free to make any assumption in which part current will flow in which direction. That will be completely your assumption, and there is no need to consider magnitude of these resistances or the magnitude of the EMFs or their directions and all that. Which side is higher, which side is lower. Nothing to be considered. Just assume any direction starting from any point as far as the circuit is concerned. The only thing that you have to keep in mind is whatever direction of the flow of current you assume in any part of the circuit, okay, the sum of current at a point it has to be zero. It means you must follow the condition of the first rule, Kirchhoff's first rule. The sum of the current at any point of the circuit, it has to be zero, or at any junction point. So if I suppose consider the current coming from this side, current coming from this side, and current coming from this side, it means with respect to this point, all those three currents will become incoming current. That I can't take, because sum of three positive quantities can never be zero. And the Kirchhoff's first rule says the summation of current at any point, it should be zero. It means at least one current you have to take in the opposite direction, so that if two are with the positive sign, the third negative sign, then the combination of all those can be zero. That is the only thing that you have to consider. Otherwise, you are free to assume any direction. So let us say I take this current I1 from this side, I2 here, sorry, I2, and this is I3 from this, in this direction. Okay. I could have taken this I1 here, I1 in this direction. Don't get again confused that I1 I have taken, so I1 is moving only up to this part, or this side it is higher, and that's why I have taken I1 this side. I could have taken I1 in this direction. It hardly matters. That completely depends on your choice. Repeatedly, I am saying, as far as distribution is concerned, you are free to choose any direction, ignoring the higher potential side and lower potential side of the cell, ignoring their magnitudes, ignoring the magnitude of the resistance. Just have your choice. Only thing, when you distribute, the first rule has to be justified. That is the only condition. Otherwise, it is up to us which direction should I take. Now, suppose I1, I2 and I3 are taken in this direction. After simplifying, I get I1 with the negative sign. If I get I1 with the negative sign, that means actual direction of current I1, it is not in this direction, but it is in this direction, not from this right to left, but it is from left to right. It means whatever sign we get for I1, I2 and I3, if you get I1, I2 and I3 with the positive sign, that means whatever we have assumed here, that is correct, and the current will flow in that direction. If you get I1 with the positive sign, I2 with the negative sign, and I3 again with the negative sign, that means I1 will be flowing in this direction, I2 in the opposite direction of this, and again I3 also in the opposite direction of this. So that plus and minus sign will finally decide what is the actual direction of the current. If you get positive sign, it means your assumption, the current is in the direction of your assumed current. If it is with the negative sign, it means the current direction is in the opposite direction of your assumption. So this is the only thing that we have to consider once the final direction or the final output is calculated. Now, based on this assumption, let us form the circuit equations. So first I will name this circuit. Let us say this is your A, this is B, this is C, this is D. And suppose this is E and this is F. Let us take this. So if you consider the circuit or the equation, first circuit, let us take this A, B, F, E, A. I choose the path A, B, F, E, A. Suppose I take this path. So it means I'm moving from A to B, again from B to F, F to E, E to A, and so on. So A to B. So A to B. So current I1 is from A to B. So it means I1 into small r1. All resistances, sum of potential difference, that is IR. So I1 R1. I1 R1 plus. Here also we have the same direction. So plus I1 R1. Next, we are moving from F to E. So F to E. But your current I2, it is moving from E to F. We are moving from F to E. That is taken with the positive sign. That the current in this branch is moving from E to F. So it will be minus of I2 R2. So minus I2 R2. Okay. Again, small r2 here. So again minus of I2 R2. So minus of I2 and R2. It should be equal to how much? Sum of all EMFs in the circuit chosen. So we have taken this circuit. We have not taken the entire circuit. We have taken this part of the circuit. So in the sum of all potential difference in this circuit, sum of EMFs in the chosen circuit. So sum of all EMFs. So this E1 is having tendency to release current in this direction, and the path chosen is also from A to B, and this is also having tendency to release current from A to B. It means E1 should be taken with the positive sign. So E1 is positive. Again, E2 here. This E2 has again the tendency to release current in this direction, because if you consider this closed circuit, inside of the circuit, so it has the tendency to release current like this. It means in this direction. When we say this, it means it will be moving like this. Or tendency to release current, it will be in this. So E2, it has tendency this side, but our path is what? F to E. F to E. So again, it is in the opposite direction of the path chosen. So it is minus of E2. So this is your circuit equation as far as this circuit is concerned. Okay. Similarly, we can consider the next circuit. The next circuit is what? E, F, C, D, E. So now in this circuit, E, F, C, D, E, we have the equation again, I2 small r2. So I2 r2 plus I2 capital R2. So plus I2 capital R2. Next it is C to D. You can see E to F, F to C. There are no resistances, so there is no need to analyze this. Now next it is C to D. In this C to D, again this is I3 in this direction and R3 here. So plus I3 R3. I3 small r3. So plus I3 small r3. It should be equal to again sum of all EMFs. So here let us say E to F, we have this cell E2. Now in this circuit you can say we are moving from E to F, and this has also tendency to release current in this direction. Now we are considering this. So this is the inner circuit. So here you will consider this. Don't now confuse this one. When we are considering this circuit, it has a tendency to release current like this, always higher to lower. Here also it is higher to lower. But this, with respect to this becomes your higher to this lower. So it has the tendency to release current in the direction assumed, that is E to F. So it means plus E2. So plus E2. This you can see. Here E2, it was taken with the minus sign because with respect to this, it was moving in the opposite direction of the assumption, because our path was F to E and current was from E to F. F to E and current means the tendency of the cell to release current, it was from E to F. So here it was negative, but the same thing here it is taken as positive because we have taken the path E to F, and this cell is also having tendency to release current in the same direction E to F. So it is positive. Now let us come to E3. E3 has tendency to release current this side, but we are moving from C to D. It means in the opposite direction of our path chosen. So it will be taken with a minus sign. So minus of this E3. So now we have these circuit equations. From the point rule, that is from the first rule, you will get I1 plus I2 minus I3, that is equal to 0. I1 plus I2 minus of this I3, because with respect to this point, this becomes your incoming current, this becomes your incoming, and this becomes your outgoing. So I1 plus I2 minus I3 is equal to 0. Now simplifying this equation, and this equation, we can calculate all the unknowns, because there are three unknowns, I1, I2, and I3. And three unknowns, we need three equations. So first equation, second, and the third. Just simplifying this, we can calculate whatever is the required quantity. So I think it is clear how to distribute the current, how to develop the circuit equations. Once we have this, after simplifying, we can calculate whatever is the